In this example problem, we're going to analyze a person standing on a scale in an elevator. Uh, we have several different scenarios with different accelerations, and we're going to look at what happens to the forces acting on this person in the different scenarios. So it really tests your ability to draw free body diagrams and evaluate what the forces are acting on that person. So let's just start here with part A. We have the elevator at rest, right? So I'm going to draw a free body diagram, and we're looking to figure out what the scale reading says. And let's look at the person here. We're going to set them in here. Technically, they're in an elevator, right? But really all we care about is the person, right? So the elevator really doesn't matter at this point. We're just going to draw the person and they're on a surface. And if that elevator is not moving, we would say that the velocity is 0. More importantly, the acceleration is 0. Right? When the acceleration is 0, we know that the net force, or the sum of all forces, is also 0. Right? And that's going to inform how we're going to draw our arrows on the free body diagram. Right? So I'm always going to start, I'm going to draw the force of gravity, Fg. And since this person is not accelerating, they're at rest, then we know that there must be another force that's balancing them out. Well, that's the surface pushing back. Right? In this case, the surface they're standing on is the scale. Right? And we're going to call this the normal force. So when they're talking about the reading on the scale is our normal force. It's a great way to think about how the normal force works. It is the force of a surface pushing on an object. And so anytime you're thinking about what the normal force would read, imagine that object sitting on a scale. If we're going to use a scale properly, you're going to stand motionless. You're not going to move. Right? But if you start jumping around on the scale, the number is going to bounce around because the normal force is what the scale is going to be pushing back on you to balance those forces out. In fact, if you leaned a scale on a wall, it would still read a value. It wouldn't be your normal weight, but it would be a value. It'd be what the wall is pushing back. So I use this example problem to really give you a sense of how the normal force can actually change. In a lot of problems, the object is going to be on a surface like this. You're going to see gravity and the normal force as equal and opposite of each other. They are not third law force pairs because they are different types of forces. But because they are the only up and down forces and you're not accelerating up and down, then they're going to be balanced, right? So this is going to happen a lot. Well, in this case, what they're trying to find is what is the normal force? Well, that means that the sum of those two forces has to be 0. So since there is no acceleration, we know that Newton's second law says that the sum of all forces cause the mass to accelerate. And the only forces we have are the normal force and the force of gravity. So I have Fg plus Fn. I'm just adding the forces, summing the forces. That causes the mass, get my colors right here, to accelerate, right? So that's really what Newton's second law says in this scenario. Well, if I want to know what the normal force is, I better know what those other things are. So in typical problems, we're going to organize our variables. We're going to have an object with mass. They tell us the mass is 64 kilograms of the person. We're going to have an acceleration. In this case, we realize they're at rest. And since we're at rest, we know we have 0 acceleration. It's not changing velocity. There's no velocity, and there's nothing to indicate that it is changing. And then we have forces, right? We have our force due to gravity, and we're going to have our normal force, Fn. And in this case, the normal force is what the scale would read, so that's what we're trying to find. Well, that means we need to know what Fg is. Well, Fg is always equal to the object's mass times the acceleration due to gravity. So in this case, it's 64. And there's a downward force of gravity, which is why on my diagram I get a negative value. If I take 64 times 9.8, I get 627.2 newtons. It's going to be a downward 627.2 newtons is what the force due to gravity is. And that matches my free body diagram. I have a downward arrow. Well, if it has to be added to something in order to add to 0, if I take this equation and I start plugging in my values, well, then I have the force of gravity is downward at 627.2. I'm going to be adding the normal force to it, which is what the scale is going to read, and that has to equal the mass, which is 64, times the acceleration. Well, that's equal to 0. Well, that means the normal force would have to be upward at 627.2, right? Pretty obvious here. 627.2 would be what the scale would read. It would read the normal weight in this scenario. It's exactly how you would want to weigh yourself. You'd stand on a scale, not move, and it should read what you normally read. But what happens if the elevator starts to accelerate? Well, that means the person is accelerating upwards. Well, let's draw a free body diagram for part 2. Now, I'm going to have a person still standing on my surface, the scale, except the velocity is now changing, right? We have an upward acceleration, right? And therefore, we must have an imbalance of forces upwards, right? And so I'm always going to, again, start with my force due to gravity, Fg. However, somehow we got to get a bigger force. Well, if you can imagine yourself looking down at your feet when you're riding an elevator and it goes up, you kind of feel heavier for an instant, right? And that is because your normal force is increasing. You actually have a bigger normal force than the force of gravity. The scale would read more than your normal weight when it's accelerating upwards, right? Because the sum of those forces have to cause that acceleration, right? So if I was organizing my work, again, I have the same mass of 64 kilograms. But we now have an acceleration upward at 1.7 meters per second squared. Our force due to gravity. Well, we haven't left the planet. It doesn't matter how we're accelerating. It is still downward at 627.4 newtons. And therefore, we better have a new normal force to balance that out, right? And so this is where having an acceleration changes our equation a little bit. But it's the same one we just used over here. We're going to have, if I draw out what I have gravity acting down, 627.4, plus my normal force, Fn. I'm just summing the forces. The sum of the forces is equal to the mass, 64, times the acceleration, positive 1.7. I'm always careful to put the signs with any vector quantities. Acceleration is a vector, right? So when I multiply 64 times 1.7, I get 108.8 is on the right side of the equation. This is 108.8. That is the net force. That is how much leftover force you would need in order to cause that acceleration. Well, that means I need to solve for Fn. So I'm going to add 627.4 to both sides. And that's how much bigger Fn's got to be. Fn's got to be 108.8 bigger than Fg. And I end up with a normal force that is upward. If I add 108 plus 627.2, I think it's 0.2. I think I was writing 4s in there. Close idea. I get 736. I think these should be 2s in here. I'll just clean that up a little bit. Not trying to confuse it. It's rounding error. These are little rounding inconsistencies here. All right, and when I add that, I get 736 newtons. Well, does that answer make sense? Well, my normal weight is 627, and now when I'm accelerating upward, I got 736 newtons. All right, so I should look like I'm heavy. I get a perception of feeling heavier. We call that feeling of having excess G's, G forces, or when you kind of get squeezed in. And you get this opposite effect in scenario C, where the acceleration is downward. You can imagine the feeling when the floor starts to drop away from you. You start to feel like your stomach is kind of rising up. You feel lighter, and that's because you have a downward acceleration, which means you have a net force that's downward. Well, again, gravity can't change. You're on Earth. That arrow remains the same. And what changes is how hard the scale pushes back. The normal force, the scale reading has to be less if we're accelerating down. Right? So I can set up my same equation here. I'm just going to simplify a little bit here. And I'm going to have that gravity, which is still downward at 627.2, plus my normal force is equal to my same mass. But now we have a downward acceleration of 1.7. Here's where the sign comes into play again. Negative 1.7, which means on the right side, we actually have negative 108.8. And so when I add 627 to that, I should get a smaller value than 627. So if I have 627.2, and really I'm subtracting 108.8, I end up with 518.4 upward at 518.4 newtons, right? It's still an upward one. I get a positive value, but it's smaller than the gravitational force, right? Which makes sense. I would feel lighter, 518.4. Right, so here we see the changing normal force, what the scale would read due to these different accelerations. All right, let's look at scenario D. I'll draw it right over here. We have an elevator moves up at constant velocity. So we know my velocity is now upward. However, it's constant. Well, what does that mean for the acceleration? Because when we draw a free body diagram, the acceleration is what matters. Well, constant velocity means that the acceleration is zero. And if the acceleration is zero, then the net force is zero, which means all the force is balanced. But let's draw that free body diagram. There's our surface. We have gravity, Fg. Well, if the forces are balanced, well, that means the normal force is equal to Fg again. So we actually have the same answer. This is the same as when we're at rest. So we should expect when we're at constant velocity, it feels exactly the same as being at rest. So I'm back to the 627.2, right? And when you ride an elevator, think about it. When you feel like you're moving, you feel it right at the start when you accelerate. But then as you're moving up, you actually don't feel anything. You feel like you're just standing in a small room because you're not accelerating. And that feels the same as being at rest. Similar to being in your car or on cruise control on the highway. As long as you're not turning, you can sit there and close your eyes. You might feel like you're parked, right? Because you're at constant velocity, which tells you that the next question should also be the same. It doesn't matter whether you're up or down, left or right. If you're at constant velocity, then you are not accelerating. And therefore, in this case, you would feel your normal weight. All right, let's look at scenario F. What happens when the cord is cut? Well, in scenario F, the cord is cut. We are going to be in free fall, right? And if the cord is cut, you're on a surface, but everything's falling. And if everything's falling, there's no surface force that can push back. And therefore, you are going to be accelerating due to gravity downward, right? And if that's the case, well, you won't feel anything from that surface. The surface can't push back. There is going to be no normal force. You're going to be experiencing 0 G's. You're going to feel weightless, right? The feeling of weightlessness is when the surface can't push on you, right? And so this is a scenario where in free fall, even though you're in a room, the floor is there, it can't push on you. So you get no force due to the scale. You would look weightless, all right? So if you've ever held a ball, they have some of these free fall rides at carnivals. You put a ball in your lap, and the ride drops. The ball looks like it's just going to float in front of you. It would have no apparent weight because your hand would not have to push on it at all. All right, so here's a bunch of different scenarios where we really look at what happens to the normal force when objects are accelerating up and down. And it really hopefully highlights the importance of understanding that the normal force is what a scale would read if that surface was a scale. And if you get that concept, I think you'll be fine when you draw these free body diagrams and think about what you would feel like standing on that surface. Would you feel your normal weight standing at rest? Would you feel like you're squeezed into the floor when you're accelerating upwards? You'd feel heavier, longer FN. Or you might sometimes feel lighter, right, as that elevator slows down. Or if you go over a rise in a hill, you kind of have that stomach sinking feeling, right? You feel a little bit lighter. The scale value would go down. And if you're in free fall, whether you're in an elevator or not, there is no surface force pushing back on you. So you get no normal force. So I hope this helps kind of highlight some of these concepts.